All right, so remember this week is the FixIt week. So if you've donked up a lab or a hack or two hacks, because we've doubled the hacks for the honor section, you can go to help hours. You can go to your regular lab or help hour or hack session and demonstrate it. The full logistics are posted on Piazza, but you have up until the exam this Friday to take care of that. After which, the grades will stand. And then, of course, after the first exam, the guardrails come down, and we won't be probably doing that going forward. So make sure that you take advantage of that if you need to, and then be prepared for the exam this Friday. Again, it opens up at 9:30, and we will not be here. I will not be here. You can feel free to use this room if you want to, but otherwise it will be 2 exercises. Do 1 in Java, do 1 in C, your choice, and there will be graders available on code post for both of those. And if you just want to do all 4 versions, right, go ahead and do that too if you want to. But otherwise, we'll only grade 1, right, 1 of each. So we left this off last time talking about how to modularize code, and in C, that was kind of involved because we had to separate it out into different files. One for the prototypes and documentation called a header file, and then we had a source file, .c file, and then we included things just like we include the regular math library, except that we use these double quotes. Then we compiled in phases. We had to compile our library, and then we had to compile whatever used our library. And that was kind of opaque to us when we first started out because it just automatically brought in those standard libraries. But now that it's not a non-standard library, a user-defined library, then we have to follow this little bit different approach here. Right? Then we followed that up by looking at Java, which was a little bit easier, right? All we had to do was separate it out into a different file entirely, right? So I took the, when we left, I went ahead and made just a regular old factorial, and then remember we'd use this big integer, big factorial, and I attempted to use big decimal, but it just was too much of a headache. Basically, you have to define precision manually, and it was just going to be way too many lines of code. And so I just went with just sign Taylor normally here because that's not the point. Right? So in any case, when we did this in Java, we separated them out into utility classes for now. Remember that everything is public. Static means that it belongs to the class, and therefore it's just a utility class that you can use just like the math library. And then classes themselves are organized into packages. Packages are nothing more than directories and subdirectories. So when we say unl.soc, there is a directory called unl, and under that there's a subdirectory, subfolder called SOC, School of Computing, right? And you separate things out into different directories. Right? You can do the same thing in C, but we won't be going there. Usually what you do is you put it into different directories, and then you have to define the rules for compiling. By the way, look for it over there in that directory, or look for it over there in that directory, instead of the current working directory. But we're not going to get that complex. Instead, what I wanted to do is, now that we've got a unit called a function or a method, we can talk more formally about unit testing. And again, a unit more generally is any piece of code. It's usually a function that can be tested. You want a unit as small as possible. It could be, with respect to Java, it could be an entire class, right? That's your unit. It could be an entire library. That's your unit, all right? But usually you want a unit as small as possible because you want to test it, right? A unit is an indivisible piece of code that you treat it as a black box, right? Stuff goes in, stuff comes out. You don't look inside the black box. That's why we call it black box. You can't look inside, right? You don't look at the inner workings of that black box. Instead, you just feed it input, and you get output, right? And a unit test for that unit is an input-output pair that is known to be correct. So, for example, if I'm trying to compute the sine, right, sine of 2.5, how do I know what the answer should be? Well, I pull out a piece of paper, right, and I start doing this by hand. Or I pull out a calculator that I have a high confidence is correct. Or I go to Wolfram Alpha or something like that, right? I need to write that input-output pair generally before, and this is called test-driven development, we even write our code, right? We don't run it on our code, we don't have an input, run it on our code, that's a black box, get that output and say, oh, well, that must be it, right? No, we're not gonna trust our code. That defeats the entire purpose of testing. The way that we test is by feeding this input into our unit, a function, and comparing the result to the known correct output. We usually call this the actual versus the expected. If they match, we say that that unit test passes. If they do not match, we say that it fails. Now you might immediately ask yourself, well, wait a second, what happens if the unit test is wrong itself? And that's possible, right? That's called a false positive or a false negative, right? They could, the output, the actual output and the expected output could both be wrong, but they agree, right? In which case it passes. That's called a false positive. It could be that the output is correct, but our expected output is wrong. In other words, we wrote the test case wrong, in which case it fails, but it's not our code, it's the test, right? That's a false negative, right? And you do have to be careful with those. Here is a visualization that's in the book, I think, where we've got maybe not, maybe it's just in my lecture for the pre-prepared video. But basically, this is a unit test, right? Here's my test case, which is an input and an output. We feed that input into our unit, get our output. That's the expected output. We compare that to the actual output to the expected output. If they're equal, then we say that it passes. If they're not, then we say that it fails. Pretty straightforward flow diagram here. Right? We want all of our test cases to pass. And we want as many test cases as possible, because no matter how many test cases you have, it is not a proof that your program is correct. You'd only have a very high confidence that your program, that your code is correct, right? We can then take multiple unit tests into one collection and call that a test suite, right? So if I've got 5 unit tests, there's my test suite, right? We want as many of them as possible. We want to do this because in the future, if there's a bug, right, great, that gives us a new test case. Right? We know that there's a bug because, wait a second, it gave this as input, but it gave me this as output, and that looks wrong, right? Okay, well, what should the output be? We take that, put it into our test suite, and now we debug it, we fix it, and now it's part of our test suite, and we can actually run it over and over and over again, right? A future change that breaks unit tests is known as a regression. So we've got a bug, right? I want to go and fix that bug. Great, now for that one unit test, now it's passing. But my changes caused all of these other unit tests to start failing. Right? That's called a regression, right? It's the opposite of progression, right? We're making progress, we're fixing bugs. Oh, we fixed a bug, but now we regress. It's the opposite of progress, right? It's 1 step forward, 2 steps back. And that's why, and so we have what's called regression testing, that we run it on all of the previous test cases automatically to make sure that it still passes all of them, right? If it passed before, that is, right? Another design principle of this is that tests should be repeatable. In other words, if I take your code and I run it on my machine, the tests should all still pass, right? It shouldn't be dependent on a machine or dependent on the time of day or something like that. It should be repeatable. In other words, it should be predictable. For this reason, we generally try to stay away from randomly generated inputs or outputs or stuff like that. Instead, we like hard coding our values, and that's what we'll do when I show you how to do this. Right? Again, the more tests you have, the higher certainty that your code is correct, but no amount of tests will ever give you a 100% proof that your code is correct. There are programs, or there are programming languages that try to do something like this. They're proof-based, what is it called? Proof-based programming languages? There's a term for it that I'm not remembering off the top of my head, but basically you write a program and then you write a proof that that program is correct, and a program verification, because then the last step is that the program verifies its own correctness. However, that still has a limitation. right? And it's deep mathematical limitation called the Gödel's incompleteness theorem, that no axiomatic system can, or set theory or axiomatic system can prove its own consistency and stuff like that. Don't worry about that, right? This is not a math class. Instead, the more tests you have, the better code coverage you have. So, for example, the tax program that you wrote a couple of weeks ago, right? There were like 5 different tiers of taxes. What if you wrote tests to only cover 3 of those cases, right? You're never testing these other 2. We want good code coverage. That means that you should have at least a test case that tests each one at least once. Then you should have test cases for edge cases and corner cases. Things that, like what happens when they enter a negative value for their income, right? What happens when they enter negative value for their the number of children that they have, right? Etc. And for those, you want corner cases, edge cases, extremal cases. What happens when that function blows up at 0, right? We want to make sure that we're testing for that. And you generally stay away from it, but you can have what's called fuzzing, right? Or sometimes, I think Netflix called it chaos testing, or randomized testing. Basically what you do is you try to feed a bunch of random crap into your code and try to break it. And if it doesn't break, right, at least it runs, right, then it's resilient. They called it chaos testing at Netflix. It's called fuzzing. There was a word before that. It's called chaos testing at Netflix because they said, what happens if those 3 servers in Seattle goes down, right? Are people going to still be able to watch their shows over in Missouri or something, right? And so they tried to inject some chaos testing. We'll just go ahead and shut the server down randomly, right? They do it under controlled circumstances, not in production, but they want to make sure that their code has a fallback, that it then starts serving from a different server, right? You don't. Well, okay. So one, you don't. Fuzzing is just trying to break it and causing it to fail, like crash completely. Otherwise, what you can do is what we do. A/B. It's not A/B testing, but what you can do is you can write 2 solutions. Right? I write a solution. I have an LA write a solution, and there are 30 solutions here, right? And if 30 solutions are disagreeing with my solution, I probably know where the problem is, right here, right? But if my solution and 29 solutions all agree, and there's one that doesn't agree, I know where the problem is right there, right? So democracy, democratic code. Now that's not always the, that's the case in education, but in the real world, you're not gonna have a boss say, let's hire 30 people and write 30 solutions, and then we'll take a vote on it, right? But you can write 2 and have one person do one and another person do another, and then hey, our code seems to agree, so it must be correct. Okay, now which one is the better one, or something like that. And then that way you can just generate random code or random inputs, feed them both in. If they match, then it passes, right? And that's kind of what we do in a lot of our tests, especially the ones you'll not see them anymore because code post is limits. The way that we're using code post is limiting the number of tests, but we used to run like millions and millions of tests from our code to your code. And then, of course, it's never the case where 999,999 things pass and that one thing fails, right? It's going to be 999,000 things fail instead. It's always going to be like that, right? It's either wrong or it's right, usually, right? It's not 50% right. All right, so again, the false positive and false negative that I mentioned before, here's the formal definitions. A false positive is when a test case is wrong, but the code is correct. Right? It's saying that it fails, but that's not correct. The code is good. Right? A false negative is when there is a bug. Oh, did I get this wrong? A bug in your program, but your tests do not indicate it. Yes, I think that these are correct. I always get them wrong, backwards. I'll look that up, but I'm pretty sure that that's correct. Anyway, you also have something called TDD, or test-driven development, where you can get so pedantic about it that you'll have people that are proselytizing and trying to get people to, you should only ever write your tests first. You should write 50 tests, and then only and then should you go and write your code, right? I don't subscribe to that philosophy. I think that this is a process that goes back and forth, right? You write some ad hoc tests on a whiteboard or something like that to understand how the code should be written, right? And then you go and write your code, and then you go back and you do some testing, and you add some more tests, and you go back and forth and back and forth. You refine your code, you go back and forth. Test-driven development assumes that you're writing all the tests correctly up front. No testing assumes that you're writing all the code correctly up front. Neither one of those assumptions is ever correct, right? So I don't subscribe to test-driven development. Instead, I go back and forth. So what I want to do now with the rest of our time is let's do an informal unit testing framework in C, and then we'll do the same formal unit testing in Java. Over here, let me go ahead and get rid of this. There we go. Yeah, go ahead.
What's the difference between informal unit testing and formal unit testing?
Good question. So informal unit testing, we're going to write our own stuff here. All right. In particular, I'm going to write. I'm not going to use. Let's see. What demo? What is that? What we were using? Okay. Yeah. I'm going to go ahead and just grab all this stuff because I'm going to use some of the boilerplate. But what I'm going to do is I'm going to write my own checks. Like kind of you saw this in lab 3 where you were testing is leap year, right? We had a chunk of code that checked, and then we had another chunk of code that checked, and we added them all up. We wrote our own basically informal unit tests, and that's what we're going to do here. And then I'll show you the formal way of doing it. You don't write all that boilerplate stuff. You bring in a library to do it, right? All right. So new file, mymath_test. Right? You usually separate these things out into separate files because you don't want testing stuff mixed in with your production stuff, with your actual code. So I'm going to go ahead and get rid of everything that I don't need. There we go. I'm going to bring in my math library though, and we're going to test it. Let's go ahead and get rid of all of this. The first thing I want to test is that Taylor series. Right? Or actually, no, the first thing I want to test maybe is that factorial. Right? So let's go ahead and test that. Int expected. Right? Here, int input. Let's go ahead and compute the factorial of 6. Right? There we go. My expected value is, what is 6 factorial? 120? Okay. Int actual is going to be a call to my function, factorial of input. There we go. Now I need to check, is that correct or not? If the expected is equal to the actual, right, then we say that it passes. Printf passed. There we go. Otherwise, we say that it fails. Failed. There we go. All right. There's 1. And here is the informal part.
I think it's 620.
Oh, it's 620? Okay. Oh, it's 720, isn't it? 720. All right, there we go. All right. Otherwise, we would have known right away. There's our false negative, right? It didn't pass, right? Cut, paste. Uh-oh. Can I declare the same variables over and over again? No. So let's go ahead and rethink this. There we go. And I could go ahead and declare them up here, or I could go ahead and input expected and actual, and then I wouldn't need to worry about redeclaring them everywhere. Already we've got an improvement. There we go. But ultimately we'll have the best improvement by not writing this stuff ourselves. What else should I test? Okay, -1. What should we expect there though? Did we write that up here? No, it's not well defined yet. So I'm going to hold off on that testing until after the exam. We'll talk about error handling instead. Right? That's an error condition. I don't want to do that. But one corner case would be 0. What's the factorial of 0? 1. Right? Okay. And now that I've got this in a nice little, format here, I can go ahead and cut, paste, and I only need to change 2 values, right? So generally, cut, paste is bad, but that's actually what you do with testing. And even with formal unit testing, that's what you do, right? What's 4 factorial? 24? Right. Okay. Let's do this. Let's bring this all together. Now remember that you need to compile oops, I'm in the wrong directory. Right. You need to compile mymath.c. There we go. That produces a mymath.o. Where is it? Mymath.o, right there, right? And now I can bring all that together with GCC mymath.o, and I'm probably going to need the math library, but I'll save that to the end. mymath test and -lm. There we go. Let's run it and see if all my code is correct up to this point. Passed. Excellent. Well, that still requires a little bit of human intervention because I have to sit there, pass. Okay, great. All of them done, right? So let's go ahead and improve this even more. Int num passed equals 0. Int num failed equals 0. And now every time I pass, I will say num passed ++. And every time I fail, I'll say num failed ++. Now let's go ahead and replace this entire code with that code. All right, there we go. And then I can have a summary at the end, right? Printf passed %d and the line, num passed, num failed. There we go, num failed. And then you can even print a percentage, right? How many did it pass? Because all I'm really interested in is like not pass. I just want to see 100%, right? Because then I'm done, right? And I don't have to worry about anything. Only when it's 90%. Oh, okay. Now I need to start looking at those aberrant test cases. Percentage, %f and the line. And I will say, oh, by the way, how do I get a percentage in printf? I can't use percentage because that's a placeholder. So, yeah, use 2 of them. Another alternative in some languages, I think Java is going to be an escape sequence like that, but don't worry about it. All right. Well, what's my percentage? Passed divided by, num passed, excuse me. Divided by num passed plus num failed. Be careful. These are all integers, so what's going to happen? Integer truncation. So we just double one of them. Recompile, run. Oh, wonderful. 1%. Oops. So what should I do? Multiply by 100. There we go. And then I don't need the typecast either. 100%. Excellent. All right. Well, now let's test that other one. Right. So my input, unfortunately, is no longer going to be an integer. So let's go ahead and declare some more variables here. And I'll just call it input _d, right? That's a terrible name, but it's generic. 2.5, right? And my double, here, let's declare them all together. Expected d and actual _d. There we go. And my input _d is going to be that. My expected _d is going to be, I don't know. At this point, I mean, we were doing all that math in our head before because factorials are easy. But at this point, what's the factorial, or what's the sign of 2.5? Right? I don't know. That's when you pull out a piece of paper and you start calculating it by hand, or you take the easy way and go to Wolfram Alpha, pull out your calculator, do whatever you're going to do. Right? In fact, this is called mocking, more generally, generating test data, mock data, fake data is called mocking, and there are entire libraries to do it for you. Right? So what is sign of 2.5? 598472. So 5.598472. There we go. And the actual D is going to be, what did I call it? Taylor sign of input D. And let's go ahead and grab all of this code and repeat it, except that I want underscore D on those two things. Okay? Yeah, go ahead.
Shouldn't we be careful about how many digits we're going to?
Save that. Save that idea. What was wrong? Undefined reference. Sign Taylor? Taylor sign. Okay, fine. Oops. There we go. All right. I want this to fail. It failed. Now, first of all, before we put that out of our minds for a second, why? How did it fail? Why did it fail? I don't know. All we're saying is that it failed. Right? So let's go back and change this message. I want to know why this failed. Right? The input is going to be %f, expected %f, but got %f. There we go. At least we'll know the values for this. And my input underscore D, my expected underscore D, and my actual underscore D. There we go. And in fact, I should probably go back and replace all these things. Do you want any more information after it's passed? No. This is my input, this is the output, this is the expected. Okay, I don't need to worry about those things. I do need to worry about it if it's failed. So more verbose error messages like this, right? More information is always good. I expected 598472, 598449. Okay. Right? Remember, we're using a Taylor series. Right? And we're only using, what was it? 6 terms here. So either we need to bump up the terms, or we need to say, that's close enough. Right? That's where we build in a tolerance. Right? I don't want to say that these two things are equal. I want to say, are they close enough? And blank are close enough. Dot, dot, dot. Now, what do I mean by close enough? Well, do you remember the AGM, the arithmetic geometric mean? When did we stop? When they got close enough, when they were within 0.0001 of each other. Right? So how do I do that here? If their difference is less than some value, something like that. Right? Now, then they're close enough. Right? If they're not close enough, then we go in more terms, or we build in a higher tolerance. Okay? Except that, well, all right, what about this minus? Remember, it's telescoping. So this could end up oscillating between positive, negative, positive, negative, positive, negative. What if it's -10? Is that within our tolerance? Not technically, but it's going to be true here, right? Because -10 is indeed less than 0.0001. So absolute value. Abs? Careful, is that correct? Abs is good for integers. I want a floating point abs in C, so that's going to be fabs, or fabs fo or something, right? These are doubles, so fabs is good enough. Right? And in fact, I don't want to hard code this, because I'm going to go ahead and do this again with, I don't know, not this part, but 3.14159. What is the sign of pi? Isn't that the easy one? Is it 0? I don't know either. 14159. Yeah, look at that. It's getting so small. Right, there we go. It's essentially 0. All right. So 0 if it's close enough. I don't want to hard code this, because what if I build in a tolerance here and then I want to change it later? Let me go ahead and replace that with a variable, and replace this with a variable. And I'm going to put that way up at the top. What should I call that variable? Okay, I like that. I was going to initially call this what calc folks would call this, epsilon or delta. But if you don't have that kind of background, right, that calc background, call it what it is. Tolerance, but you got to spell it correctly. There we go. And then you can change it in one spot. Tolerance and tolerance. All right, so does that pass all of our stuff now? Because I'm not including the math. Now I am doing math stuff, so I need to include the regular math library. There we go. Now imagine if I was doing this in an ad hoc manner, making these changes, having to go back and redo this every single time, or hit one button and I run all those tests, no problem. Passed, 5, failed, 0. Now, that is an informal way of doing things, writing your own boilerplate code. You see a lot of this is just cut and paste, cut and paste, cut and paste. Right? There's got to be a library out there to do something like this for me, and there is. Yeah?
When you include at the top and you include the packages, what's the difference? Like, the angle brackets are
The standard libraries, the ones that are defined by the language. And then these are either user defined, I define them, or if I were to bring in another library from whatever, right?
that's just with anything else.
Yeah, include, I mean, you could get away with this. Here, let me show you. You could get away with this. The problem is that the compiler is going to think that it's a standard library. Oh, it is fatal now. Okay. And it's going to be looking in the wrong place. Right? And it used to be that you could get away with that, but not anymore. I think that, let's see, maybe you can get away with this. Don't quote me on this. Let's find out. Okay, you can get away with that. But don't do that because it's a bad practice. It's, yeah, you could get, it ends up finding it in the correct place just by not chance, but this sends me a signal that these are standard libraries. This sends me a signal as a user, as a programmer, oh, this must be a custom library. Right? That's the idiom.
There's also the question with the when it passes, why don't you put the outputs there? Because how do you know it's not false?
Good question. Well, you could. I mean, the only thing that's going to end up being printed is the input, which you wrote it, the expected output, which you wrote it, and the actual output is just going to be a repeat of the expected output. Right? So, yeah, if you wrote it, then you seem to know what you're doing. So no reason to output it. Unfortunately, with the formal unit testing framework that we're using for C, it also doesn't even do this for you. It just says it failed on line 5. Now I've got to go back and find out why it failed. But fortunately, there are much better ways of doing that in other languages. Over here in Java, I could go ahead and cut and paste everything that I just did. I'm not going to do that. Instead, I'm going to show you a formal unit testing framework in Java, which is going to be JUnit. And for us, it's going to be version 5. Okay? So in Eclipse, the way that you can bring this in is right-click. What is it? Build path, add libraries, and JUnit. There it is, right there. JUnit. Next, you can go ahead and choose an older version. I would not recommend that. JUnit 5 is now very, very mature. Finish that off, and you now have JUnit as part of your project. These instructions are repeated in Hack 6 when you actually need to use them. But otherwise, what I can do now is I can go ahead and create a test function. So here's my math, which is in UNL utils. I'm going to go ahead and create a new class called myMathTests. Right? Because it's going to be test suite. I don't have any problem with pluralizing this. Right? Okay. All right. I never remember the syntax, so I'm going to have to look over here. Right? Anyway, let's go ahead and repeat some of these tests. For example, the factorial of 6 should be 720. So let's go ahead and create a function. Public void test factorial, and I'll just call it 001 because I'm going to have a bunch of tests. Okay. And my input here, I'm going to grab some of that code. Right, there we go. I'm just going to grab this code right here. And my input, I can put these into variables. I don't have to if I don't want to. My expected is going to be 720, and my actual is going to end up being my math dot factorial of n. And there's the input. Oh, it's a long, sorry. Long, I did change it to long and long. Remember, those are just twice as big. They're 64-bit integers instead. Still positive, negative, but we can represent up to, what was it, 9 quintillion instead of 2.147 billion. Now what I'm going to do is I'm going to use the library to test whether or not these things are equal or not. And so I'm going to say assert equals expected and actual. There. I'm going to have to bring this in. Add static import for assert. Yeah, assertion. Which one is it? I need to look it up. Assert equal. I'm just going to grab this code. I don't know if this is it or not. Nope, it's Jupyter. Excuse me. Anyway, when you get to Hack 6 and Lab 6, when we show this to you formally, it'll all be there. Anyway, I'm just importing this function that checks these things, and it'll end up automatically taking care of all that boilerplate for me. If I add another test, for example, let's just go ahead and cut and paste this one. Right. Call it 2, and we'll do 0 and 1 here. Right. There's another one. So another cut, paste, but the boilerplate of adding up all this stuff and reporting the results is taken care of by the framework itself. Here's something brand new. I have to label this as a test. Is there anything, other than the name, there's no way of indicating that this is an actual test. So I'm going to annotate this and call it a test. I'm going to annotate this one and call it a test. And this is also from Jupyter. So let me bring this in. There we go. Org, JUnit, Jupyter, which is the project, the API, and then the test. Okay. This is, if you want to ignore me for the next 2 minutes here, this is magic. All right. So now, what is this thing? This thing is an annotation. It's something. So what we've been doing up to this point is called structured programming, where you write functions and then you have statement, and it runs, right? Sometimes you have loops, sometimes you have conditionals. You also have things that are called object-oriented programming, where you orient yourself towards objects and object communication. You have something called aspect-oriented programming. And this is aspect-oriented programming, where I'm saying, you know what? I want to force this thing to become a test. So I'm just going to annotate it and say, framework, you take care of all the code generation for me. And it will automatically go and generate code that looks something like this in the background to actually achieve what we did over here in C. Right? And it's an annotation. It takes care of all of it for me. It's really, really powerful. It allows you to avoid a lot of boilerplate stuff, and it goes beyond tests and unit testing frameworks and stuff like that, etc. So it's an aspect-oriented programming. Common solutions can be annotated, and you don't have to worry about writing any code. Right? This is a test. There's another test. There's another test. There's another test. Right? Now, how do I actually run this? Same way that you run any program. Hit play. Now, over here, you don't go at the console anymore. Instead, a brand new tab will come up called JUnit. Let me go ahead and increase the size there. So runs, 2 of 2. How many tests did I define? 2. How many errors were there? 0. How many failures were there? 100%. Cool. Right. By the way, you can double-click a tab to expand it, double-click it to put it back down. Right. What if I had yet another test? Give me another value. 4, I think it was. 24. I'll call it 3. But without that annotation. It's just a function sitting out in the ether. It's just sitting there. That's not, a JUnit is not going to recognize it. 2 of 2 still. Right? Because I did not annotate that as a function at test. There you go. Now I will have 3 out of 3, and hopefully everything passes. Green means good. Right? Let me write a bad test here, 124, and you'll see what happens when something fails. Red. Actually, that's a really dark red magenta. And that's not a magenta. What is it? Maroon. Thank you. It's a maroon. Right, there we go. And you'll understand that, and it even gives you an error message like we wrote. Right? Can you read that down there? Expected 124, but it was 24. There we go. I can double click on that and I can look over here. There's the expected, there's the actual. Again, it was wrong, right? I can go back, fix it, and run it again. Play. Now it's 3 out of 3. Right? Formal unit testing framework, JUnit. What about that tolerance thing? Right? Let me add another test here. So public void test sign, Taylor sign, 001. You can give these more descriptive names if you want, but this is usual. This is unfortunately the usual way of doing things. Label your tests because it really doesn't matter. I'm not going to put it into the function name that says test factorial that tests 4 as an input and 24 as the output. Just 003. Yeah.
I'm just curious, would it be possible to potentially automate the naming of test cases?
I would, good question. There are better ways of doing it. And I have an example here of the better ways of doing it? Let me, here's the Java. Actually, this you'll see it later. I'm just cribbing this stuff here. So here's a JUnit test for lab 6. There we go. So I want all those test cases, right? There are a dozen there, but I don't want to write a dozen damn functions. So what I did is I put it into another annotated test. This is a parameterized test. Here, I'll zoom in here. There's a parameterized test. And I want you to run this on a bunch of arguments, right? And if any one of them fails, then this entire test fails. I want you to run it on these arguments, these, where the first 3 are the inputs, and then the last one is the expected output. So yeah, I don't like writing code either. If I can write it compactly like this, and then let the aspect-oriented programming take care of those details for me, I do it, right? So yes, but that goes a little bit beyond what I wanted to show today. But check it out, right? Anyway, let's go ahead and take a look at the test of sign. So let me go ahead and grab one of our things. Here it looks kind of like this. So there we go, double, there's my input, double expected, double, and I don't have to use underscore D here because these are completely different functions in completely different scopes. And so I can reuse those variable names. Now here, if I just used assert equals, it is going to fail. What is it, my math? Sign Taylor, there we go. Let's run it, and we're gonna see that it fails. Oh no, oh, forgot the test, there we go. There we go. Yep, it fails. Why? Again, if you look at this, it expects, here's the expected 598472, 59847, and then a whole bunch of change. All right? So there are other utility functions that you can use. And this is where I was cribbing it from. Isn't there a tolerance? Fine. Tolerance. Fine. There we go. Assert equals, and then we build in a tolerance here. I don't know, 0.001 is what we used or something. And is that compiling? Yeah, that should compile. There we go. Now everything works. There's just another assert equals here that takes a third argument, the actual tolerance that you want to build in. And once again, I'd probably put this into a variable called tolerance. And let's put that up at the top so that we only have it in one location. Public static final tolerance, final double tolerance is equal to that. There. Now, public, anybody can see it. Static, it belongs to the class. What is this final keyword doing here? Do we remember?
It's like the definition in C.
It's like define in C. It's defining a constant. You cannot redefine this later on. If over here I want to say tolerance is now equal to 2, right? That ain't happening because it's final. It's a double floating point value. Why did I go all caps there? Same reason I did all caps for kilometers to miles or whatever it was. It's a final. It's a constant. So we're going to use a different convention here to indicate that, no, this is it. It's a fixed value. Right? Just like math.pi, right? Or math.e or something. Run this once more to make sure that it works. Great. Once you're set up and running on a unit test framework, again, what do? Cut, paste, cut, paste, cut, paste, cut, paste. One disadvantage of doing what I showed you before of these CSV sources is that all 12 of these are treated as one test. And so if any one of those 12 or whatever they are fails, the entire thing fails. Now, if you're paid by the test, maybe separate those out and say, oh, no, instead of just getting a 0%, oh, okay, well, one of those tests failed. Now I'm getting 90%. And that, you're playing a numbers game at that point, though, right? Don't do that. Look for the cheapest possible solution. Question?
So like it won't tell you, it'll just give you 100% or 0.
Exactly. Yep. It'll probably tell you which one of these values expected this, but I got this. It'll tell you that, but oh, whoa, what was the input? Let's check that out. Let's try breaking this again, and let's see. Does it get us any more information? No, but at least it tells you what line number it's at. You can double click it and jump there. Okay, well, it's this test. There's something wrong there. So, JUnit for the C version of the formal unit testing framework, we use something called CMACA. Mock, like mock test data, like I said, and it's why a C? Well, because it's C programming language. And Maca, it used to be called Mockery when Google ran it, and then as Google famously does, any great project that they put together, they eventually abandon. And so C Mockery was abandoned. Open source folks took it over and renamed it CMACA. Right? And it looks something like this. Hey, assert an integer not equals. That looks mighty, mighty familiar, right? You're going to follow these same patterns over and over and over again in every language. It's got a bunch of inputs and it's got an expected output. Down here, where do we bring everything all together? We've got all these tests. We add them all to the CMACA unit test pre-states, right? And then down here, we finally run them all. And it gives you a summary report at the end, just like over here in JUnit. Yeah?
What does code post use?
Good question. So I have to write them all. So in some instances, I write my own. I've written my own kind of like this. In other instances, I have written a JUnit test framework. And in fact, on a lot of those instances, we give that to you as your future lab. Now, once we introduce you to it, so that you can run your lab right there with the JUnit, and you'll see 100%. You turn it into code post, and it runs the exact same stuff. Otherwise, for the C version, I do use CMACA in some cases. Otherwise, I tend to roll my own for the C one because for various reasons. It's all brought together. The only language that they allow you to use is Bash. So I have to write a bunch of Bash scripts. And that's why it doesn't always look all that great. Like the expected input and the expected output, I have to write Bash scripts to produce that crap. So it's not, like I said the other day, there's a term called, or there's a idiom maybe, called there's no such thing as a free lunch, right? You use one thing, there are advantages and disadvantages. You use a different thing, there are different advantages and different disadvantages. You always have to, at the end of the day, you have to pick your poison. You have to pick the one with the least bad disadvantages and the best advantages. And so there's no such thing as a free lunch. You're always paying for it somehow. All right, we will do we'll do exam 1 from last year on Wednesday.